Universal Asynchronous Receiver and Transmitter. UART. This is a demonstration of a full duplex asynchronous transmission. The C8051F226 microcontroller is capable of a UART function. These are the TX and the RX pins. For the F226 microcontroller, the TX and RX pins are shared with the port function. The UART function is selected through the UART enable bit in the PRT0MX register. The reception enable bit in the SCORN register is also set to enable serial reception. Let's take a look at the UART circuit inside the F226 microcontroller. This is the TX pin and the transmit circuit. This is the RX pin and the receive circuit. The baud rate generator logic is used to generate the TX and RX clock in order for the transmission to take place. Let's set up the operation mode of the transmission. Let's select asynchronous mode, using timer 1 or 2 as the baud rate clock. This setting is done through the SCORN register, using the SM0 and SM1 bits. SM0 and SM1 are set to 0 and 1 respectively. Reception enable is also set. The rest of the bits are cleared to 0. This is the required setting of the SCORN register. Let's take a closer look at the operation of the baud rate generation logic. The operation mode is set to mode 1, where SM0 and SM1 is 0 and 1 respectively. SM0 and SM1 select these set of multiplexes. These inputs are selected. Therefore, the transmission clocks are taken from the output of the divide by 16 module. The T clock and the R clock signal are controlled by its respective bits in the T2 CORN register. These bits are 0 by default. Therefore, the 0 inputs are used. S-mode signal is controlled by the S-mode bit in the P-CORN register. Its default value is 0. Therefore, the transmission clock is taken from the divide by 2 module. These are the settings for the control registers. Let's assume we want to set the communication baud rate to 9600 bits per second. The transmit and receive clocks need to be 9600 cycle per second. The clock feeding the divide by 16 module needs to be 9600 multiplied by 16. And the clock feeding the divide by 2 module needs to be 9600 multiplied by 16 by 2, which is 307,200 cycle per second. This clock is fed from timer 1 overflow, which means that timer 1 needs to overflow 307,200 times every 1 second. Let's take a closer look at timer 1 operation. Timer 1 can be set to operate in 8-bit, 13-bit, or 16-bit. Timer 1 will be set to 8-bit as a baud rate generator. The setting is done through the timer mode register. These 2 bits will determine the timer mode. For 8-bit operation, it is set to 1 and 0. This is the logic circuit of timer 1 operating in 8-bit mode. In 8-bit mode, only TL1 will be counting. The content in TH1 can be set to any value from 00 to FF by software, and its content is used to load TL1 whenever TL1 overflows. What does that mean? Let's set TH1 to FA hex. Observe carefully when TL1 overflows. Whenever TL1 overflows, the value in TH1 is loaded to TL1. Let's assume our system clock frequency is 11.0592 MHz. The clock feeding the timer is the system clock divided by 12, which is 0.9216 MHz. This gives a clock period of 1.085 microseconds. Assuming TH1 is programmed with content FA hex and TL1 starts counting from FA hex. Every count increment is 1.085 microseconds. When TL1 overflows, it is loaded with FA hex. The counting continues from FA hex. How much time does it take the timer 1 to overflow after the previous overflow? It took 6.51 microseconds. Timer 1 overflows every 6.51 microsecond. How many overflows are there in 1 second? Take 1 second divides by 6.51 microseconds. In 1 second, there are 153,610 overflows. This number is called the overflow rate. Timer 1 overflows at a rate of 153,610. This clock goes through a divide by 2 and divide by 16 modules. The clock that reaches the transmit and receive modules eventually is 4,800. Therefore, this setting provides a transmission and reception baud rate of 4,800 bits per second. We had initially wanted a transmission rate of 9,600 bits per second. So how to set up for this baud rate? Timer 1 has to be configured to overflow 307,200 times in 1 second. So how often should timer 1 overflow? Take 1 second divides by 307,200. Timer 1 should overflow every 3.255 microseconds. What should be loaded to TL1? In order for timer 1 to overflow in 3.255 microseconds, remember, the count increments every 1.085 microseconds. Take 3.255 divides by 1.085. It only takes 3 increments for timer 1 to overflow. Therefore, TH1 should be set to FD hex in order for timer 1 to overflow every 3.255 microseconds. Setting TH1 to FD hex will provide a baud rate of 9600 bits per second. Let's write the program to configure the serial communication. First, the TX and RX pins need to be selected through the UART enable bit in the PRT0MX register. The reception bit in the SCORN register needs to be set to 1. The serial communication mode needs to be configured to configure timer 1 to 8-bit mode through the T-mode register. Set TH1 to FD hex for a baud rate of 9600 bits per second. Set timer 1 running using TR1.